Okay, thank you very much. Yeah, hopefully I'm still audible.
Yeah,
So
perfect.
yeah, I'm very grateful to the organizers for this fantastic workshop, and I'm also quite grateful to the talks that have happened before, because that will lay the foundation and the theoretical aspect of this work. So I won't dwell too long on those aspects and jump straight away into the results. So like the title suggests, what we did here, me and my collaborators listed on the right-hand side, what we did was we searched for the stochastic gravitational wave background in the gravitational wave data from LIGO that was made publicly available and pertaining to the second observing run. For your information, this work has been published, and I've put down a couple of references at the bottom. So if you wish to have additional details, please do take a look at these publications. All right, so I hardly need to spend time on this slide, but very quickly, primordial black holes are expected to have occurred in the early universe due to primordial curvature perturbations, specifically over densities in those curvature perturbations. They are expected to span a very broad mass range, with the minimum mass being as small as 10 to the minus 5 grams, and they're predicted by many models of inflation. The nice thing about primordial black holes is that they have the potential to answer a number of long-standing astrophysical and cosmological questions, including seeding supermassive black holes, sources of gamma ray bursts, and perhaps most importantly for this workshop, they are an excellent candidate for dark matter. Now, the kind of primordial black holes that this particular talk focuses on are a class of primordial black holes called ultralight, where by ultralight we basically mean masses that are less than about 10 to the 15 grams. And this boundary is basically set due to Hawking radiation, where the expectation is that primordial black holes with masses less than about 10 to the 15 grams would have evaporated by the current cosmic age. Now, based on Hawking radiation, there have been a number of interpretations of data from different experiments to put constraints on the abundance of these ultralight primordial black holes in the ultralight regime. So these experiments include extragalactic photon background, Big Bang nucleosynthesis, among others, CMB also. But the thing that I would like to emphasize here is that Hawking radiation has to date not been verified experimentally. And therefore, it would be interesting if we can come up with constraints that are independent of Hawking radiation. And that's kind of the focus of this talk. All right, so the primordial black holes that we will be focusing on in this talk span about 10 to the 13 grams to 10 to the 15 grams. And associated with the primordial curvature perturbations that source these primordial black holes, you also have a stochastic background of secondary gravitational waves induced by scalar-scalar mode couplings. And therefore, we are in a potentially nice situation where if we search for this stochastic background, we can put constraints on the amplitude of the pertaining power spectrum. And from this constraint on the amplitude, we can put constraints on the abundance of ultralight primordial black holes, and this would be independent of Hawking radiation. So I guess the main question that this talk tries to address is, can we search and detect this stochastic background in LIGO Virgo data? All right, so in order to start off with doing such a search and putting constraints, we need to make an assumption. So we need to assume what the shape of the power spectrum is going to be. There are a number of popular shapes out there in the literature, including monochromatic, top hat, among others. The shape that we choose is basically the log normal or Gaussian shape, as I've put down over here. It has a central wave number, and it has a number of hyperparameters, including an amplitude, a width, as well as a central wave number. So all these are effectively free parameters, and by varying 2 out of those 3 free parameters, we can then put constraints on one of them. So that's the procedure that we are going to adopt. Moving on to the next slide. So like I'd mentioned before, the power spectrum sources the stochastic background of gravitational waves, where the stochastic background is typically expressed as the energy density per logarithmic frequency bin rescaled by the density required for a flat universe. So that's the first equation that I've put down over here. The general expression for this omega GW is fairly complicated and doesn't have a closed form solution. So therefore, it is instructive to actually plot them and see what they look like and at what point they actually peak. And we can compare that with the sensitivity curves of the detectors to see whether we should be able to detect them or not. So that's what I'm going to do in a couple of slides. So as you can see over here, you have on the left-hand side a plot of omega GW for a narrow spectrum, sigma equals 0.1, and then the plot for omega GW for a broader spectrum. And you have different cases for the central wave number, or equivalently the PBH mass scale. And what you notice is that for PBH mass scale spanning about 10 to the minus 18 to 10 to the minus 20 solar masses, we find that these spectra actually fall within the sensitivity curves of the LIGO detectors. Now, the dashed brown line is the sensitivity curve that you would expect at LIGO's design sensitivity, and the purple curve corresponds to the sensitivity curve at the second observing run. So this basically seems to motivate that it might be actually worth doing a search even in the second observing run and come up with some sort of constraints on the amplitude and therefore the abundance of primordial black holes at the time of their formation. All right, so once you have constraints, once you have a detection, or in fact even a non-detection of the stochastic background, you can put constraints on the amplitude. From there, you can put constraints on the abundance at the time of formation, which we denote as beta prime. Now, from beta prime, you can also derive what is the mass function at the present day. And from the mass function, you can then derive the fraction of dark matter as primordial black holes at the present day. All right, so this slide I've already talked about. So moving on, so these are prospective upper limits that you would get, assuming that all your detection are either at 2 sigma, meaning SNR of 2 or below. So this is sort of the prospective upper limits that you would get from different observing runs using the noise power spectral densities that have been projected for these different runs. And what essentially you see over here is that at the second observing run, you are already competitive with existing constraints, although in a certain, only in a very limited region of parameter space. But as you will go to the future observing runs where the detectors become more sensitive, your constraints become stronger and span a broader range of masses. And by the design sensitivity, the constraints will become extremely strong, many orders of magnitude stronger than what you would get from other non-GW experiments that depend on Hawking radiation. All right, so moving on then, hopefully this is sufficient motivation that it would be a good idea to actually start searching from whatever data is available today. So LIGO has made the second observing run data publicly available. So the way that you actually search for the stochastic background, the way that you search for omega GW is using a method that involves the so-called cross-correlation statistic. The cross-correlation statistic is given in the left-hand side box that you can see on this slide. It basically takes the Fourier transform of the data from 2 detectors. In this case, it would be LIGO Hanford and LIGO Livingston. It also depends on a geometric parameter called the overlap reduction function, denoted by gamma t. And from this cross-correlation statistic, you can actually derive an optimal statistic called omega ref, which is given below, and that depends on the cross-correlation statistic as well as its variance. And using a particular weight that I have put down at the bottom of on the left-hand side, omega GWF ref divided by omega GWF, as well as the cross-correlation statistic and its variance, you can construct an SNR. And the nice thing about this SNR is that it is directly interpretable as a significance. So
Sorry,
for
Shasvath,
example, if, yes.
you have 2 more minutes.
So the SNR has, so the SNR, if it has a value of 1, it will correspond to a 1 sigma event. If it has a value of 2, it will correspond to a 2 sigma event, and so on. All right. So moving on, then you can also do parameter estimation on the hyperparameters and construct a posterior on the hyperparameters. So what we do over here is we construct a posterior on the amplitude, and by taking its 95% upper limit, we can basically put constraints on the power spectrum, and from this 95% upper limit, we can also put constraints on the abundance of primordial black holes at the time of their formation. All right, so this is the first set of results. These are the search SNR, which I just talked about. What you notice over here is that the search SNR can be, the largest search SNR that we got over this parameter space was approximately 2.7. Nevertheless, this is not very significant, because if you include a trials factor, the significance of these events actually goes down quite a bit. And in fact, we repeated this exercise by injecting in Gaussian noise. And what we found is that the data, if you just have stationary Gaussian noise, is consistent with what you get when you do the search, suggesting that there is actually no signal in the data. All right. Now, like I mentioned, you also have a likelihood, and therefore you can construct upper limits on the amplitude as well as the abundance of primordial black holes, and that's what you see over here. The takeaway point from this slide is that only for a certain region of the parameter space, you are doing better than existing constraints from Hawking radiation. Nevertheless, this is already quite promising, because like I mentioned, by the end of the third observing run and the fourth observing run, you will do significantly better over a broader parameter space. And this is kind of the main result put in the context of the different other experimental constraints. What I have put in the shaded regions are the constraints from our work. Again, it basically says what I had said in the previous slide. Only for a narrow region, you get constraints that are marginally better than the existing constraints currently available, but they should get significantly better with future observing runs. And these are this is my concluding slide. What this basically tells you is that we had the very first GW data-driven constraints in the ultralight regime, which should get much better with future observing runs. And the nice thing about these constraints is that they are Hawking radiation independent, and so they should nicely complement the constraints that are already existing in that regime. Thank you.
Thank you, Shasvath, for a nice talk. I don't see any question in the chat box as of now. So if the participants, any of the participants have any question, I can ask him or her. Okay, I find one question from Subinoy. Okay, so Subinoy, if you want, you can just unmute yourself and ask the question.
Shasvath, so I have a naive question. So do you have any constraint on the fraction of dark matter, or it can be the 100% of dark matter in this mass range?
Yes, we have constraints on the fraction of dark matter. So this is, so that was actually this slide over here. So this is not the abundance at the time of formation, but this is the constraint on the fraction of dark matter. But again, there is the caveat that if you put your results in this way, you have to neglect Hawking radiation.
So what is the percentage? I can't read it out.
Oh, I'm sorry. So we can go down to as low as 10 to the minus 15 already for certain regions. So the purple means that we have hit FPBH equals 1. But if you look at the sort of brown and pale brown, so these are basically 10 to the minus 12 to 10 to the minus 15. So you get very, very strong constraints in these regions of the parameter space. But they are, like I mentioned, in very limited regions. This will get much broader once we get into the third observing run, where the data was from detectors that were much more sensitive.
Okay.
Okay, that's great. I find no more question over here. So let's thank the speaker once again.